So far this week, you've learned how to create an equivalent circuit model of a battery cell that includes open circuit voltage that is dependent on a cell state of charge. In this lesson, you will learn how to add elements to this model that describe voltage polarization. Polarization is a term that refers to any difference between the measured terminal voltage of this cell and the cell's internal open circuit voltage due to the passage of electrical current through that cell. For example, you probably know that a battery cell's voltage drops when the cell is under load. And this voltage drop then can be modeled, at least in part, as a resistance in the circuit that's placed in series with the ideal voltage source. I've placed a diagram of this modified circuit on the right-hand side of the slide, and you can see the resistance that has been added is denoted by the label R0. And adding this resistance changes the voltage equation to be equal. Cell voltage equals open circuit voltage as a function of state of charge minus the electrical current multiplied by R0. Now note that this model, even though it's quite simple, is common enough to have been given a name, and in the literature you will often see people refer to this model as the R-int model. And this name indicates that we're including a description of the internal or int resistance of the cell in the model. Now, if you look at this equation and think about it a little bit and remember that electrical current is considered to have negative sign when we're charging the cell and positive sign when we're discharging the cell, then this equation really begins to make sense. You'll see that the voltage at the terminals of this cell is greater than the open circuit voltage when we're charging, which is what we expect. And you will also notice that the cell terminal voltage is less than open circuit voltage on discharge. And if you weren't sure what to expect, you could consider what happens when you're discharging the cell and you measure the voltage and then you remove the discharge current. You find that the voltage immediately jumps up. And so therefore, while you were discharging, the voltage had to be lower than the rest voltage. Now, the addition of this resistor also explains why energy efficiency is not perfect. We know that the power lost through a resistor is equal to the current squared multiplied by resistance, and so having a non-zero resistance means there's power lost due to heat, and so energy efficiency of a battery cell is not perfect. This simple R-int model is vastly better than the previous model. Because the previous model did not include any measure or metric of the cell resistance. In fact, this simple model is often good enough or sufficient as a basis for creating simple electronics designs for circuits that include battery cells. But when we're building a battery management system for an advanced consumer electronics application or a vehicle application or a grid storage application or something where we require a really accurate model, this still is not accurate enough. The term that we've just added to the model multiplies electrical current by internal resistance, and it models the instantaneous voltage response to a change in the input current. But in practice, we also observe non-instantaneous responses to change in input current. And I refer to these non-instantaneous responses as dynamic responses. So that is, a battery cell's voltage will continue to evolve over time due to some previous change in input current. The figure on the right-hand side of this slide shows an actual lab test. It shows the measured cell voltage for a lithium-ion battery cell that is initially resting at a high state of charge at a little over 4.1 volts. The test begins with the cell simply resting. No current is passing through the cell for approximately 5 minutes. And then after 5 minutes, we apply a constant current discharge to this cell that lasts for about 15 minutes. And then the discharge current is removed and the cell is allowed to rest for the remaining 40 minutes of the test. Perhaps you can see that the instant in time that discharge current is applied to this cell, the voltage responds with an immediate decrease. And we can model that in part using the series resistance R0. And then we see that for the first 15 minutes, the 15 minutes during which we're discharging this cell, we can see that the cell voltage is continuously decreasing, but at a slower rate than that instantaneous drop. Now, we also know that cell state of charge is decreasing while we are discharging the cell, so we might at least think at first that this voltage change is due only to the open circuit voltage of the cell changing as we're discharging it. And it is partially due to that, but it is not only due to that. So when we allow the cell to rest after time 20, notice that the voltage does not return immediately to a constant open circuit voltage, but the voltage instead gradually changes in a process we call relaxation. The voltage relaxes toward a constant open circuit voltage. This relaxation of the terminal voltage toward open circuit voltage appears to take at least 40 minutes to occur. And this phenomena is not described by the equivalent circuit model that we've developed so far. If you think about the model that we've developed so far, the instant we remove discharge current from this cell, the state of charge stops changing. And therefore the open circuit voltage instantly stops changing the moment we remove current from this cell. And the voltage drop across the internal resistance, R0, instantly drops to 0. So there's nothing in our present model of the battery cell that has any kind of time constant like we observe here of this relaxation that takes 40 minutes to achieve its final value. So we'd like to enhance the existing battery model by including equations or terms that describe these slow time constants. We might also like to understand why this is happening. Why do we observe this phenomena of the slow change in voltage? And it turns out that this slow relaxation of voltage is caused by slow internal diffusion of lithium from one part of the battery cell to the other, where concentration gradients built up while the cell was being discharged, and they have to slowly relax back to their equilibrium values. And because diffusion is a process that does not happen instantly, the cell's voltage does not change instantly to its final value either. And so I refer to this slowly changing part in voltage as a diffusion voltage. It turns out to be relatively straightforward to modify our circuit diagram to include a description of these diffusion voltages. What we do is we add a parallel resistor capacitor branch in series with the current path of the battery cell. And a modified circuit diagram including this resistor capacitor branch is drawn on the right-hand side of your slide. The new resistance is labeled R1 and the new capacitance is labeled C1. And notice that we don't throw away the instantaneous resistance R0 or the state of charge dependent voltage source. We're adding components to describe this new phenomena that we're thinking about now. This revised circuit model is known as a Thevenin model. And with this revised model, we can now compute cell terminal voltage as equal to the open circuit voltage as a function of present state of charge minus the capacitor voltage and minus the cell electrical current multiplying R0. And we can also write the cell terminal voltage equation in a slightly different way. We can compute the cell terminal voltage as equal to the open circuit voltage as a function of state of charge minus the voltage across resistor R1 instead, and minus the voltage drop across resistor R0. Notice that resistor R0 carries the full cell load current, but resistor R1 does not carry the full cell current at every point in time. The cell current is split somehow between the current that passes through the resistor R1 and the current that passes through capacitor C1. So when we compute the voltage drop across resistor R1, we need to write that voltage drop as equal to the resistance R1 multiplying the current that passes through that resistance only and not multiplying the entire total cell current. Now, this equation describing cell voltage may look a little more complicated than the earlier one, but it turns out that writing things this way makes the process of identifying or computing parameter values for the model based on tests that we conduct in the laboratory a lot simpler. And so I'm going to write this equation in this way from now on. So now we have a proposed circuit that we believe will help describe or explain the diffusion voltages, but we have to come up with equations that describe the current that passes through resistor R1. And in order to do this, notice that the entire cell current is divided between the current that flows through resistor R1 and the current that flows through the capacitor C1. And if we open our linear circuit textbook, we can discover that current flowing through a capacitor is equal to the value of its capacitance multiplied by the time derivative of its voltage. This allows us to write the current split as the current passing through resistor R1 plus the current passing through capacitor C1 is equal to total current, or the current passing through R1 plus C1 times the time derivative of capacitor voltage is equal to total current, which is what we have here. We also notice that the capacitor C1 is in parallel with resistor R1, so they have to share the same overall voltage by Kirchhoff's voltage law. So we can replace the voltage across capacitor C1 with the equivalent relationship to this, and that's equal to R1 multiplying the current through resistor R1. And that allows us to rewrite the previous equation as shown. So that is the current passing through resistor R1 plus R1 times C1 times the time derivative of current passing through R1 is equal to the total current. Now notice we have a ordinary differential equation in the current passing through R1, and we can reorganize the terms of this equation so it's a little bit more clear that this is indeed a first order standard ordinary differential equation. And I've done that on the bottom of the slide, and you can see the time derivative of current passing through R1 is equal to the negative 1 over R1 C1 times the current passing through R1 plus 1 over R1 C1 times the overall battery current. So this brings us to the end of the development of the Thevenin model of a lithium-ion battery cell. And this new Thevenin model improves upon the previous model to include a simple description of voltage polarization. So at the beginning of this lesson, you learned that we should add an equivalent series resistance to our earlier model, and we called this series resistance R0, and we called the model the Rint model. And this was an improvement over what we had studied earlier, but it did not yet describe dynamic changes to voltage. It described only instantaneous changes to voltage when the input current changed. The Thevenin model improved on that because it adds this resistor-capacitor subcircuit in order to model diffusion processes in the lithium-ion battery cell. And you'll see later this week that we can actually add multiple resistor-capacitor subcircuits to our model to even improve further upon what you've seen in this lesson. So putting everything together that you've seen so far, the equations here show the entire Thevenin model in one place. And the model has one differential equation that describes the evolution of state of charge, and this is the same equation that you saw in the previous lesson. The model has an additional equation to describe how current passing through resistor R1 evolves over time. And finally, the model has an equation that combines information from the state of charge and the R1 current to compute the overall cell voltage. The first two differential equations are known as the state equations of the model, and the final equation is known as the output equation of the model. The equations that we have developed so far and what you see on the slide are all for a continuous time model. But as you've learned already, the battery management system algorithms most commonly require models that are expressed in a discrete time form instead. So you're going to learn how to convert these equations from continuous time into discrete time later this week.